Salam, everybody. So we're starting off with physics, October November 23, paper 4-2. Let's begin. The first question after the data booklet is define the radian. So you know that the radian, you need to memorize the definition. It's the angle subtended by an arc at the center of the circle when your arc length and radius are equal. And you should know what is arc length and what is radius. So if this is part of a circle, this is arc length, this is radius, and this is the angle. And this angle is 1 radian when S, which is arc length, and R, which is radius, they're equal. Remember the definition. The minute hand of a clock revolves at a constant angular speed around the face of a clock. Now, one thing you need to understand, the minute hand, it takes 60 minutes to travel one complete circle. Does that make sense? It takes how much time? It takes 60 minutes to make one complete circle or one revolution. So how many seconds does it take? It takes 3,600 seconds, which is 60 into 60, for one complete revolution. And one complete revolution would mean 2 pi radians. Now, if you go back to the question, the first thing that they're asking you for is the angular speed. Angular speed is 2 pi over t. The time period, as I explained, is 3,600. So 2 pi over 3,600 would give you 1.7 10 to the minus 3. Now, during a time interval of 1400 seconds, bear in mind that one rotation is 3600 seconds for the minute hand. So they're saying 1400 seconds. So this is definitely less than one revolution or one complete rotation. How much angle have you covered for 1400 seconds? So for 3600 seconds, we know that the angle that we cover is 2 pi. 2 pi is equivalent to 360 degrees. And 1400 seconds, it'll be x, so you can just cross multiply the two. So 3600x, I'll just do that over here. 3600x should be equal to 1400 into 2 pi. And you can calculate the value of x by making x a subject, and I've done that over here. Your answer will be 2.44 radians. Moving on, in those 1400 seconds, the piece of modeling clay moves a total distance of 0.44 meters. So your modeling clay was here in those 1400 seconds. This is the direction of revolution. So that means you're moving like this. And in 1400 seconds, you have moved from here to here and you've covered 0.44 meters. So 0.44 meters is basically your arc length. And the question that they're asking you for is, what is distance L? What is basically this distance L? And distance L can be calculated because you know that the angle that you covered in this time, you figured out the angle was 2.44 radians. So you can just put 2.44 here. So the formula was what I wrote before over here, that the arc length, radius, and angle are linked by this formula. S is equals to r theta. Now S is 0.44, R is L, and the angle is 2.44. Remember that in that formula, the angle will always be in radians. Never put the angle in degrees. That's why they ask you to calculate the angle in radians. Alright, so 0.44 is equals to L into 2.44. You don't need the radian mode, don't get me wrong. You don't need the radian mode. Your calculator will be in degree mode. Radian mode is only needed for math. This is not a math paper. Remember, bio kids also give this exam. So radian mode is not needed. You will remain in degree mode. But for this formula, you must remember that the angle has to be in radians. It cannot be in degrees. So 0.44 divided by 2.44 will give you 0.18 meters. Now, calculate the magnitude of the centripetal acceleration. Again, the formula you should know. Acceleration is omega square r. You can even put a negative sign with it. The value of omega you had already calculated as 1.7 into 10 to the minus 3 whole square into the length, which is 0.18, and the acceleration that you get is 5.2 10 to the minus 7. Now hold on over there and just focus on the value. Is the value very big or is the value very small? The value is very, very small. Compared to what? Look, this is the piece of modeling clay, and it is moving from here to here in a circle, as you know. So even if it moves here, there has to be some sort of centripetal acceleration, and that centripetal acceleration is giving you some centripetal force, because centripetal force is mass times centripetal acceleration. So if centripetal acceleration is small, what do you say about central force? Central force is also small. And you all know that centripetal force is a resultant force. I always tell my kids, centripetal force is always due to other forces. Now, what are the other forces? The other forces are the weight of the modeling clay or whatever this block was made of, and the force exerted by the minute hand on this clay. That's why it is over there. Now, if you go back in the question, how do I know it's over there? They say in the question that a small piece of modeling clay is attached. It's there. How is it there? The weight of this thing should move it down. There must be a force upwards, and that's the force exerted by the minute hand on the modeling clay. So there are two forces acting. One is the weight of the modeling clay, which is downwards, and second is the force of the minute hand, which is upwards. And because you know that the central force is the resultant force. Now, what is resultant force? Resultant force is always the larger force minus the smaller force. And for circular motion, that larger force will always be the one pointing towards the center of the circle. So which is the force pointing towards the center of the circle? It is the weight of the object which is pointing towards the center of the circle. So the resultant force, which is your centripetal force, will be equal to the weight minus the force exerted by the minute hand. Now, we've already decided that this centripetal force is negligible. It's very small. And because this is very small, hence your weight will nearly be equal to this F. If this is very small, that means it's almost zero. Almost. What does that mean? That the weight and the force exerted by the minute hand, they're almost the same. And that is exactly what they're asking you for. That use your answer in C3. C3, you had calculated centripetal acceleration to explain why the variation of the magnitude of this force, why is this force not varying? Why is the value not fluctuating a lot? The reason is that this force is nearly equal to the weight, and the weight is not going to change. And why is it not changing? Because the centripetal force is negligible. So these two things are nearly equal. These two things are nearly the same. And that is why the magnitude of the force exerted by the minute hand is negligible. The variation is negligible. The force is there. The force is equal to the weight. But the variation, the difference, if you move from here to here, the difference in the force is going to be very small, because the centripetal force, which is basically the difference between the weight and this, that's very small. So there's no variation. So centripetal acceleration is negligible compared to acceleration of free fall. Very important, because you have to compare centripetal acceleration with something. Resultant force is negligible compared to the weight of the clay. Again, resultant force is negligible because centripetal acceleration is small. And you could say that the force exerted by the minute hand is nearly equal and opposite to the weight of the modeling clay. And that is your answer. Moving on, question number 2. Define gravitational potential at a point. Again, definitions, memorize. There's no pardon for somebody who misses out or who forgets. These are free marks. Imagine 2 marks over there, 2 marks over there. You've already scored 4 marks in a 100 mark exam. And every mark counts. Remember, every single mark counts. Rather than thinking that I'm going to score 100, you should start thinking I'm going to score every single mark that I can. And inshallah, that will amass itself to 80 plus or 90 plus. So work done per unit mass in bringing it from infinity to a point in a gravitational field. There's no question about it. You have to memorize it. What is the gravitational potential at the surface of the moon? They've given you the mass, they've given you the radius, easy question, minus gm over r, just plug in the values, chuck, and the answer is 2.86 in 10 to the power 6. And obviously there is a negative sign, so this answer is going to be negative, and you write minus 2.9 in 10 to the power 6. And the unit for gravitational potential, because gravitational potential is basically gravitational potential energy per unit mass. Gravitational potential is gravitational potential energy per unit mass. And gravitational potential energy has unit joules, mass has unit kilograms, hence gravitational potential will have the units of joule per kilogram. And the negative sign is there because it shows that as the force is attractive, so work gets out as the distance decreases. This is another question that they ask, very common. Part B, an isolated uniform spherical planet has gravitational potential phi at its surface. A particle of mass m is projected vertically upwards from the surface. Okay, so I have something like this. I have a planet, and there is a gravitational potential phi at its surface, and there is this mass m on its surface, and that mass is projected vertically upwards. And the particle is given just enough kinetic energy, so we're talking of escaping away from the planet and without any additional work being done on it. Determine an expression for, in terms of m and y, for the gravitational potential energy. I just explained this over here. What is gravitational potential energy? It's m times phi. So it's m times phi. And show that the speed at which the particle is projected upwards. So this escape velocity is given by this expression, minus 2 phi under root. Now, just remember one thing, that when it escapes and reaches infinity, when this mass reaches infinity, its gravitational potential energy will be maximum, correct? Because height will be maximum. And your kinetic energy has to be minimum. Makes sense? It has to be minimum. What is your maximum gravitational potential energy? That's 0. And what's the least kinetic energy? That also has to be 0. So that means that when you hit infinity, your total energy has to be 0. Remember this. Gravitational potential energy, the values are negative. So if you remember the graph for gravitational potential or potential energy, it's like this. If this is gravitational potential energy versus distance, the closer you are to the planet, the more negative you are. Remember, this is distance. So this direction, the distance is increasing from the planet, which means you're gaining height. You're going up, 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 up. And usually they give this question as R, 2R, 3R. Remember? So R, 2R, 3R, what is that? It means that you're moving away. And when you reach infinity, you will almost hit this axis, so it's going to be 0. So maximum is 0, gravitational potential. And as you gain height, you're going to lose kinetic energy. And that's exactly what they're saying. That when you reach that point, infinity, escaping the gravitational pull without any additional work being done, that means that your kinetic energy will be 0 at that highest point. Escape means that you have to give it just enough push that it reaches infinity, and when it reaches infinity, it's dead. It's there. Its potential energy is maximum, its kinetic energy is 0, and it has reached infinity. So the total energy has to be 0. Now on the surface, your total energy is the sum of your gravitational potential energy and your kinetic energy. And because you know energy is conserved, so total energy initial must be equal to total energy final. So your total initial energy initial must be equal to total energy final. Your total initial energy will be kinetic energy, which is going to be half m into v escape square. That's the formula for kinetic energy, half mv square. I'm calling this velocity as v escape. So this is v escape. Plus gravitational potential energy at this point. You've already figured out the expression m phi should be equal to the total final energy, which is 0. Now do the math. You can eliminate the m's because you know that you can take m common. So cancel out this m, cancel out this m. And how am I doing it? Have a look at that. If you're confused, m common. So 1/2 of v escape square plus phi should be equal to 0. Now you bring this m down over here. So half v escape square plus phi should be equal to 0. Now do the math. Half v escape square should be equal to minus phi. So v escape square should be equal to minus 2 phi. And then when you take an under root, you will end up getting this answer. I hope it makes sense. Part C, a particle is moving upwards at the surface of moon. Use your answer in A2 and the expression B2 to calculate the minimum speed of this particle that will help it escape. So again, they're asking to calculate the escape speed. So escape speed is going to be square root of 2 phi, and surface of moon, what is the gravitational potential? That's 2.9 × 10⁶. Just plug in the value and you will get 2393, right? That has 2400. Now they're bringing in ideal gases with this. Hydrogen may be assumed to be an ideal gas. The mass of hydrogen molecule is 3.34 × 10⁻27. Calculate the root mean square speed of a hydrogen molecule. Now, you need to understand that what is root mean square speed? Root mean square speed is basically your mean square speed and you take an under root on top of it. And where does this mean square speed come from? If you remember ideal gases, in ideal gases you have this expression, average kinetic energy is 3 by 2 kT. They ask you to prove this a lot of times. So you must know how to prove. So average kinetic energy is 3 by 2 kT. K, Boltzmann constant, is 1.38 into 10 to the minus 23. Your temperature is 400 kelvins, you put here, and that is equals to 1/2 of m into mean square speed. So your mean square speed is 4.96 into 10 to the power 6. So you plug this value over here and you calculate VRMS as this number. And this is your root mean square speed. So round it off to 2 to 3 SF and you will get your answer. The surface of moon reaches temperatures of approximately 400 Kelvin when in direct sunlight. So the temperature on the surface of moon is approximately 400 Kelvins. Use your answers in C and D to suggest why the moon does not have an atmosphere consisting of hydrogen. Because so let's say this is the moon, okay, and let's say that the surface temperature of the moon is 400 kelvins, and this atmosphere is, let's say, of hydrogen. So they're saying use your answers to suggest why the moon does not have an atmosphere consisting of hydrogen. What you need to understand is something which is known as the Boltzmann distribution curve. This curve that I've drawn for you. What is the Boltzmann distribution curve? This distribution curve basically tells you that at any given temperature T, your gas molecules will have a range of kinetic. They won't have one single kinetic energy. They'll have a range of kinetic energies. And where this peak comes, this is that average kinetic energy, which is what you're talking about. So there will definitely be particles which will have kinetic energies above this average. So what are they going to do? What are these molecules going to do? Will they remain or will they escape? What's going to happen? They will escape. These ones will remain because they have speeds less than the escape speed, but these guys will escape. So molecules have a range of kinetic energies at any temperature. This is the basic premise of Boltzmann distribution. Remember this curve. It shows that at one temperature, if this is hydrogen gas, every molecule will have a different speed. One will have low speed, one will have high speed, one will have low speed, one will have high speed, and it's a distribution like this. So not all will escape, but not all will remain. So why the moon does not have, maybe most of the molecules have energies which are above this average, which is the escape speed, and that's why it does not have that atmosphere consisting of hydrogen. So hence many molecules will have speed greater than the escape velocity, and hence they escape. Escape velocity, which you calculated, was 2200. So that means that these molecules have, most of the hydrogen molecules have escape velocities above 2200. That's why they're escaping. I hope that makes sense. Now, question number 3. What is meant by the internal energy of a system? Internal energy of a system is the sum, again, it's a definition, microscopic sum of kinetic energy and potential energy of the molecules in the body which are in constant random motion. Remember this. Use the first law of thermodynamics to explain what happens to the internal energy. So delta U must be equal to Q plus W. That is the first law. What happens to this? You have to explain. Of a spring when it is stretched at constant temperature within its elastic limit. So when you're stretching, that means that you are doing work because you're giving it potential energy. You're stretching, you're giving it energy, it's stretching, it's storing that energy, and there's no question of any heat transfer because the temperature is constant. So there is no heat transfer. There's no information about Q, but you're stretching it, so that means you're doing work. So you're giving energy to the molecules, and the molecules will therefore have increased internal energy because you're doing work. Your energy in stretching is going where? It's going inside the spring molecules. So what are they going to do? They will have a higher internal energy, and that is the answer to the first question. The second one, a sample of water when it evaporates from a rain puddle on a hot day. Now this is something that I need to explain. Look, this is a puddle. You know evaporation. Evaporation is a surface phenomenon. Evaporation causes the higher energy molecules on the surface to leave, leaving behind lower kinetic energy, so causes cooling, but it causes a very negligible change in volume. Remember this, evaporation causes a very negligible change in volume. Boiling, on the other hand, has significant change in volume. And where does volume come in this equation? Think. Where does volume come in this equation? It comes here, work done, because work done is pressure times change in volume. So if I'm saying that volume change is negligible, what does that mean? Is there any work done? You will say work done is negligible. It's very small. It's very little. But for boiling, you will say a lot of work is done because the whole thing is going to evaporate. And it's on a hot day, so that means you're definitely gaining heat. That was missing over here. They never mentioned that you're gaining heat from somewhere. It's a hot day, so that means you're gaining heat. The work done by water is very little. So this work done is very small. You're gaining heat. So what's going to happen to your internal energy? The internal energy will be definitely increasing because the amount of heat that you're gaining is very large compared to the work done by this gas, by the water. The work done by water is less. And when you say work done by is negative, remember. So the reason why, if you look at the marking scheme, they're saying that you have to specify that the heat gain is greater than the work done, because if the work done was more, then the internal energy would decrease. Because if this answer is more, then this would be minus delta U. Minus delta U would mean decrease. But here, because of this word evaporation, you know that the volume change is very small. Hence, work done is small, but you are gaining heat. So that means that this number is bigger. So there is an overall increase in your internal energy. So the internal energy of the water molecule increases since the heat gain will be greater than the work done. And in boiling, work done big or small by water? I think I've answered that question already. Question number 4. An electron in a metal rod moves randomly about a mean position when an alternate AC. Okay, so it's a question on AC. So this is showing you how the displacement varies. And another important thing to note is that it's this is 0. And where is the mean position? The mean position is going to be here. Do you understand? This is your mean position. Mean position is that line which divides the curve into two equal halves. So don't make it at the 4 mark. It's not at the 4 mark. It's one step below. And this is 0. This is 2. That is 4. So this value is going to be 2.4, 2.8. This is going to be 3 points. Each box is how much? So this is 2 point. Each box is 0.4, 2.4, 2.8, 3.2, 3.6. So what is this number? This number is going to be 7.2. I've already done the math. So what is the amplitude? Your amplitude is going to be this distance. Either you can calculate this way or you can calculate this way. Both way your answer will be the same, which is going to be 3.6. But do not forget that there is a 10 to the power minus 15 written over here, which a lot of you will definitely forget. Add that in your notes. Look at the axis very carefully whenever you're doing graphs. And that's a common mistake, not looking at the graph. So 3.6 to the 10 to the minus 15 is your amplitude. What is the angular frequency? Angular frequency, omega. Omega should be 2 pi over t. So what's the time period? I've done that over here. It's basically from here to here. And this number is 0.05. This number is 0.25. So you subtract them. And again, remember that there is micro written over here. So micro is 10 to the power minus 6. So your time period will be 0.2 and 10 to the power minus 6. So omega will be 2 pi over t. So that will be 3.14 and 10 to the power 7. You could write 3.14 or 3.1, whatever suits you. Use your answers in A1 and A2 to determine the maximum speed. Now, maximum speed will always have this formula V naught is equals to omega A naught. I think this is the easiest thing that you should know. And if they ask you for speed at any other instant, and at any other instant, they will definitely tell you, like, for example, they'll say, what is the speed at this time? What is the speed at this time? They could ask you that question. What is the speed of the molecule at this time? They could ask you that question. Remember, in that case, the speed at any instant will be calculated by using V is equals to omega under root A square minus X square. where amplitude will remain the same, which is 3.6. Amplitude will remain the same. Your displacement will continue to change. Your displacement will continue to change. Remember this, okay? So your displacement continues to change. Your amplitude remains the same. Now, use your answers to show that the maximum drift speed is given by this expression. So you know that maximum speed, for maximum speed, your displacement has to be 0 because you're at the mean position. So the formula becomes V is equals to omega under root A square. So V becomes equals to omega A or omega A naught. And you know the value of A naught. The amplitude, you've already figured it, 3.6 in 10 to the minus 15. Plug that and your answer will be 1.13 in 10 to the minus 7 meters per second. Part B. The rod has a cross-section area of 4.3 centimeters square and contains a number of conduction molecules, conduction electrons, 8.5 in 10 to the 28 per meter cube. Remember, it's cm square, so you need to convert it into meter square. How? This is the conversion. 1 centimeter, centi is 10 to the minus 2. So when they say 1 centimeter square, you could even do it like this. 1 centimeter is, centi is 10 to the minus 2, and then you write meters. Meter, and centi is this. So when they say 1 centimeter square, you basically put 10 to the minus 2 meter and put a square on top, so you'll get 10 to the minus 4 meter square. Easy. Similarly, if they say 1 centimeter cube, you can just put a cube and it'll convert it to meter cube. It'll be 10 to the minus 6 meter cube. Use the answer to calculate the current. So you remember from AS that there's a definition for current. There's an equation for current, which is NAQV. And how do we know that it's NAQV? Because they're giving you the number of conduction electrons, they're giving you the area, they ask you to calculate the speed already, and you know the charge of the electron. So just plug in the values and you will get your answer as 0.66 amperes. Now on figure 4.2, sketch the variation of the current in the rod with this time t between t is equal to 0 and t is equal to 0.4. So when you sketch the variation of current, you need to understand that I explained to you that when you started off at your mean position. Understand what I'm trying to tell you. You start off at your mean position. Your mean position was this line. So you started off with maximum speed. I wrote that over here. When you're at your mean position, your speed is already maximum. How do I know it's my mean position? I'm on the mean line. It is my mean position. And at the mean position, your speed will always be maximum. So this formula is for maximum speed. So at the mean position, the current that you get is also going to be maximum. And that maximum value is 0.66. And then when your speed changes, your speed will decrease because after maximum, your speed has to decrease. So the current will also decrease with it. If you look at this over here, at t is equal to 0, the speed of the electron is maximum. That makes sense. So the current has to be maximum. So at t is equal to 0, you should show maximum current. Now, from maximum, what happens to your speed? It has to decrease. So you should go back to that graph and see when is your displacement maximum. Your displacement is maximum here. And if you look at maximum displacement, which is at 0.05 seconds, V is omega under root A square minus X square. At t is equals to 0.05 seconds, your displacement is equal to your amplitude. Does that make sense? At t is equal to 0.05 seconds, your displacement is equal to your amplitude. 0.05 seconds, your displacement is this. This is your amplitude. This is maximum displacement. So what is your speed going to be? Omega under root A square minus A square. Instead of X, you put A, so V is 0. So remember this, remember these facts. These are simple facts from SHM. That when your displacement is equal to your amplitude, which means that your displacement is maximum, your speed will be 0. And when your displacement is 0, quickly tell me, quickly. When your displacement is 0, will your speed be minimum or maximum? It will be maximum. And if I ask you, what is the formula for this? What will you say? Quick, in your head, write it down. V max is omega A. That's how clear. If you're this clear in your head, how can you go wrong in paper 4? You can't. But you have to be this clear. And if you're not this clear, try to get this clear by practicing. So V max is omega A. All right. So that's the maximum speed, and for minimum, you have to be at the highest one. And try to understand. Look, this is a pendulum. When the pendulum reaches its extreme position, the amplitude is maximum, but it stops. So what is the speed? The speed is 0. So at 0.05, the speed is 0, hence the current has to be 0. And then what happens after that? Again, it starts coming back towards the mean position. Look at this. It starts going back towards the orange line. So if it starts going back towards the orange line, towards the mean position, so your pendulum is going from this position to this, what's going to happen? Your speed will start to increase, and it'll be maximum when the time is 0.1 microseconds. So at 0.1 microseconds, you're showing us maximum speed. And that is why you get this curve, and then you keep replicating it, and that's it. Keep the time interval constant. I hope that makes sense. Use your answers in A2 and B1 to determine expression for I in terms of t. So what is this shape? This shape is cosine. What was this shape? This shape was sine. All right, this shape is cosine. You should know this. So the general formula for this is I is equals to I naught cos omega t. The value of I naught was 0.66. Omega was, you had already calculated, 3.14 in 10 to the minus 7. Because they've asked you that you want your answer in terms of t only, hence you have to write down these values. Otherwise, if you just write this, you're not going to get marks, because they want the answer in terms of t. So this is your answer in terms of t. Determine the root mean square value. Though this is your peak value. How do you get root mean square value? This is the peak value. You know that you have to divide by under root 2, and you'll get the RMS value, root mean square. Question 5. Coulomb's law. Coulomb's law, memorize. This is the equation. Just explain the symbols. Q1 and Q2 are point charges. R is the separation between the charges, and E naught is relative permittivity of free space. The value is given to you in the data booklet. Part B. Two identical oil droplets are in a vacuum. The centers of the droplets are a distance of 3.8 in 10 to the minus 6 meters apart. So I've got two droplets here and here. They're giving you the distance between them. They're giving you the force. They have equal charge and exert electric force on each other. So what is the magnitude of the charge? So they're giving you the force, which is 6.3 10 to the minus 17. You put that here. They're giving you the separation, which is 3.8 10 to the minus 6. You put that here. And the formula that I've written is KQQ. Because if you look at, I think you should, in your data booklet, you should have K as well. Let me confirm it for you. Do they give you this formula? First of all, the first thing is that you should never rely on the data booklet, because there's so many things that are not given. But yeah, this value is given. Look, this is the value of K. So the formula for force was 1 over 4 pi epsilon naught Q1 Q2 over R square. So if you're using E naught, you can use this value. But what I did was, for my whenever you're defining, define it by this equation. But for calculations, make your life easier, you can write this as K Q1 Q2 over R square, where the value of K is this 8.99 tens per 9, or you can write 9 tens per 9, and that's exactly what I've done. Let me go to question number 5. Where's question number 5? Here it is. So yeah, so I've written K, and the value of K is 8.99 into 10 per 9. That you will plug here. The charges are equal, so you can write Q square. Force and R square will get multiplied. Remember that this is R square. A lot of people forget the R square and they just multiply force with R. No, it's R square. So 6.3 10 to the minus 17 times R square, and then divide this by K. The value was 8.99 tens per 9. You'll get the value of Q square as this. Then you take an under root. This is your charge, 3.2 into 10 to the minus 19. One of the oil droplets is now placed between two horizontal plates as shown. Okay, so this is how they've placed it. The first question should be, what is the electric field? Maybe. Or what is the sign of charge on the oil? So the oil droplet is now placed, and the oil droplet is stationary and in equilibrium. Why is it in equilibrium? Because the weight is downwards, and there must be something which is pulling the oil droplet up to hold it in its place, just like that mass which we're doing in question number 1. There's this force. This is electric. And why will the electric force be upwards? It can only be because this charge is negative. So negative is attracted to positive, and that's why the charge on the droplet is negative. On figure 5.1, draw 4 lines. You know that this is a uniform field, so the lines should be equally spaced. The 4 field lines have to be equally spaced. And now the distance between the plates is 5.2, so they're giving you an idea of the electric field strength. Electric field strength, the formula is V over D. You have the voltage, which is 1200, and this is 0, so the potential difference is going to be actually 1200 minus 0. I just wrote that as 1200. Divide by the distance, which is 5.2 into 10 to the power minus 2. You get the electric field strength. Then you get the electric force as Q into E. You know the charge. The charge was... Where is it? Where is it? Here's the charge. 3.2 10 to the minus 19. So you can calculate the electric force. Once you calculate the electric force, that will be equal to the weight, and I think they're asking for the mass, so you get the mass from there. So that's exactly what they've done. Charge into voltage divided by the distance, because voltage over distance gives you electric field, is equals to mg, gravity 9.81. This gives you the mass. And what unit? What unit? All of these are SI. So what unit is this? This is kilograms. And what are they asking for? They're asking for kilograms. If they ask you for grams, you would multiply this with 1,000. Got it? Just get rid of the kilo. And question number 6. Let's have a look. Alright guys, let's have a look at question number 6. A capacitor is charged so that the potential difference across its terminals is 8 volts. And this is when the switch is initially open and the time is t is equal to 0 when you close the switch. So when you do close the switch, the capacitor will naturally discharge because there's a resistor over here. So you have 8 volts at t is equal to 0, and you know when the capacitor will discharge, the voltage across the capacitor is going to fall like that, and the initial charge is 450 microcoulombs. So first question is, show that the energy stored at t is equal to 0 is 1.8. So the energy stored at t is equal to 0 is this point. This is the charge, which is 450. And you know, it's the area under the graph which shows the energy stored. So this area, so half into base into height. So, or you can say half into V into Q. And your answer would therefore be 1/2 of 450 micro into 8, which is 1810 to the minus 6, which is 1.8 millijoules. And that's exactly what you have to show. One thing that I want to mention over here, that there is another formula for the energy stored in a capacitor, which is half CV square. But if they ask you to calculate the change in energy as the voltage, let's say, decreases from V1 to V2, then the formula will become 1/2 of C into V2 square minus V1 square. Remember that the squares will be individual. Remember this. Very, very important point. If the voltage is changing between V1 and V2, and you want to find out what is the change in energy, one way could be that you write it as 1/2 of C into V1 minus V2, or V2 minus V1 whole square. Wrong. Whenever you have a square on something and you have to take that thing twice, you always have to take the square individually. Just like, for example, you have the formula half mv squared. This is the formula for what? This is formula for what? Formula for kinetic energy. So if your speed has increased from V1 to V2 and they're asking you to calculate what is the change in kinetic energy, what will you do? You will say 1/2 of m into V2 square minus V1 square. You will not say V2 minus V1 whole square. Why? Because there is a square on top of V and you need to take that value twice and you need to take a difference between them. So you square them first and then you take the difference. And this is because A minus B whole square is not the same as A square minus B square. You know the math. So A square minus B square is different. And this is A square minus B square. This is not A minus B whole square. All right, bear that in mind. Determine the capacitance. Now the gradient of this graph, not even the gradient, because it will be the gradient if in case you have capacitance is Q over V, right? So if you have a charge versus voltage graph and it's a straight line, then you can say, okay, the gradient of the graph will give me capacitance. But you can simply do it this way. Capacitance is what? Capacitance is charge or voltage. You have the charge, which is 450 micro, and you have the voltage, which is 8. So just do that. Why do you need to apply the formula for gradient? So 450 × 10⁻⁶ divided by 8, you get 56.25, and you have to give the unit microcoulombs. Micro. Remember that. And over here, the unit is coulombs, and the value is 5.6 × 10⁻⁵. Now, figure 6.3 shows the variation with time of minus ln. Whenever you get this, whenever you get capacitors and they're giving you a ratio of voltages, remember that there's a background to this. And the background is this equation of a capacitor, the discharge equation of a capacitor, which is this one. Next, what you do is you take the natural log on both sides. Ln V is equals to ln V naught plus ln e to the power minus t over RC. Remember this? Or if you want to go by the way they're doing it, this is one variant of it. The other variant is the moment you see this, V upon V. So there's a voltage upon another voltage. In that case, you have to write the same equation, which is V is equals to V naught e to the power minus t over RC. Then you write it like this: V over V naught is equals to e to the power minus t over RC. Now you take the natural log on both sides, so you'll get natural log of V over V naught is equals to natural log of e minus t over RC. Minus t over RC comes down, so you end up getting ln V over V naught is equals to minus t over RC into ln E. Ln E is 1. So I hope that makes sense. I'll move this to a side so that you can copy it off. Now, if you're wondering that maybe this is going to give you a different answer, no, it can give you the same result as well, but it's just going to require a little bit of math, which is you'll need to write this as ln V minus ln V naught is equals to ln e to the power minus t over RC. Now, there's a log rule, which is that if you have two quantities which are being divided, you can write them as ln A minus ln B. Similarly, if you've got two quantities that are multiplying, you could write them as ln A plus ln B. So you've got two quantities which are subtracting V and V naught, and you have ln with both of them, so you can write this as ln V over V naught. It's just the reverse of this thing. So if this is V and this is V naught, this is A, this is B, you can write V over here and you can write V naught over here. So ln V over V naught will give you ln e to the power minus t over RC, which is the exact same thing as what you got here. And then you bring minus t over RC down, and now you do understand why the negative sign comes. Why does the negative sign come? The negative sign comes because, look, you have ln V over V naught, right? This negative sign goes here, and you get minus, and then this is t and 1 over and RC divided by RC. So if you have minus ln V over V naught on the y-axis, and you have time on the x-axis, what does the gradient of this graph give? Look at this. You do this. This is called linearization of an equation. So ln V over V naught is equals to 1 over RC into t. Now this thing is on the y-axis. This thing is on the x-axis, so y is equals to mx, and plus c. Plus c is nothing. So the gradient of this graph would give you 1 over RC. I hope that makes sense. And they can give you the value of capacitance, find the value of resistance, or give the value of resistance, find the value of capacitance. Have they given you the value of resistance? No. I think they will. You've already found the capacitance, right? Which is this. So if you find the gradient of this line, you put it here. You literally put in the value of the capacitance over here, and you can find out the value of the resistance. That's how this works. But let's have a look at the first question. Show that when t is equal to 1 time constant, by the way, this tau is 1 time constant, this thing, t over RC. RC is tau, and tau is called time constant. All right, so when I was writing this, instead of writing RC, I just wrote it as tau. Remember, tau is RC. And I did the whole thing, the same thing. I took V naught to this side. Now you'll understand V over V naught is equals to this. Then I took ln on both sides. minus t over tau came down. I wrote it like this. Then I took the minus sign to this side, and I got this result. Got it, which was the same as this thing. So this thing over here is matching this thing over here. Do you understand? Now look at what they're saying. They're saying when your time is equal to one time constant, which means instead of t, you write tau. So when you, instead of t, you write tau, what's going to happen? Tau and tau will get cancelled. You will get 1. So they're saying when t is equals to one time constant, the value, show that the value of this thing is equal to 1. So V0 was 8 because you know that that was the initial voltage. The initial voltage across the capacitor was 8 volts. So the value of V0 is 8. Where is it? Where is it? Yeah. So this V0 is 8. So you could have written 8 over here. You could have written 8 over here. You could have written 8 over here. Or you could write 8 at the end. Instead of V0, just write 8. And you can say that when t is equals to tau, you can put tau over here. Or you could put t over here. You could cancel them out. And you could say, well, minus ln v over 8 is equal to 1. And look at the graph. That when minus ln v over 8 is equals to, this is minus ln v over 8. When this is equals to 1, what is the value of the time? Look at this. You'll get the value of time. When you look over here, the value of time that you get is 3.2. The value of time that you get is 3.2 seconds. And when minus ln v over 8 was equal to 1, did you not say that t is equal to tau? Isn't that what they were saying? When t is equals to tau, minus ln v over 8 is equal to 1. So now you're reversing the logic and you're saying, well, when minus ln v over 8 is 1, then the time, whatever time I'm getting, the time is 3.2 seconds. If you look at it from here, this time over here, this is 3, this is 3.2. So the time is 3.2 seconds, and this will be equal to one time constant. And once you have the time constant is RC. So time constant is 3.2 R, and this is the value of C, and you can get your answer from there, which will give you the same result as if you were to take the gradient of this graph and do 1 over RC. But why do a difficult thing when you have this easy thing to do? But in some other question, this thing can actually work for you, that you can calculate the gradient of this graph. You don't have to do it for this question, but for another question, remember that the gradient of this graph will give you 1 over RC, 1 over time constant. Okay. And moving on, question number 7. A Hall probe containing a thin slice of semiconducting material is placed in a uniform magnetic field. This is a semiconducting slice. So remember, Hall probes are there to detect magnetic fields. Okay. If there's a magnetic field, the Hall probe will give you a value. It is different from a coil. Coils work on something else. You must know the difference between a Hall probe and a coil. Hall probe, if you give it a magnetic field, it'll give you a value. Coil, not necessary. We'll do coils later. It's going to come with this question. So you have a semiconducting slice, that's the material of the Hall probe, and the current in the Hall probe is 5.4 amperes. And they're saying that you get some Hall voltage. This is the current, these are the charge carriers, and this is the magnetic field, how the magnetic field is changing. So show that B is equal to this when Hall voltage is this. So you need to know the formula for this. The formula for Hall voltage is BI over NTQ, where B is the flux density, which they have given you, 4 × 10⁻⁶. I is the current, which was given to you as 5.4. I showed it to you above. N is the number of charge carriers. They were also given to you 1.5 × 10⁻�16. T is the thickness of the Hall probe, must be given to you in the question. 1.8 millimeters, convert that to meters, so 1.8 × 10⁻³ and Q is a charge, 1.6 fundamental in 10⁻⁹. You get your Hall voltage as 5 volts. Next, on figure 7.3, sketch the variation of Hall voltage. Like I said, if you have a magnetic field, you will have a Hall voltage. And if you look at this equation, Hall voltage and B have a direct relationship. Remember, Hall voltage versus time and BT have the same shape, 100%, because they have a direct relationship. You can see it from the equation. Hall voltage is directly proportional to magnetic field strength. So if your magnetic field strength is 0, Hall voltage is 0. If your magnetic field strength is 4, your Hall voltage is 5. That's fine. The values can be, I didn't say same values, I said same shape. So at 0.02, I should be showing a Hall voltage of 5. Look at this. At 0.02, the Hall voltage is 5. You can clearly see I've drawn this for you. So 0.02, the Hall voltage is 5. If I can do it here for you. So 0.02, so this is 4. Look at how I scale it. 4.4, 4.8, 5.2. What is the center of 4.8 and 5.2? That's 5. So not this, here in the middle. Yeah, here. Now let's anyway. Yeah, so this is the value. This value over here. And then you draw a straight line all the way from here. Then your Hall voltage was steady. Why? Because your field was steady. If you go back, look at your field. Your field is steady at 4. Hall voltage will be steady at 4. So Hall voltage is steady for the next 0.02 seconds. Like this. Now what happens? Now your magnetic flux density decreases from 4 to 2. So where should your Hall voltage go? They have a direct relationship. When this is 4 into 10 raised to the power minus 6, this is 5. When this will become 2 into 10 raised to the minus 6, what will this become? This will become 2.5. So we, in our voltage graph, will take it from 5 over here to 2.5. And if you look, that's exactly what I've done. You take it to 2.5. So you have 2, 2.4, 2.4, 2.8. Yeah, so 2.5 would be somewhere here, very close to 2.4. And let me just draw a guideline over there. Let's say it's here. And this is the value. This is the time value. And this happens till 0. Let me draw it from here. Yeah. The dot is ruining my graph, but you get the idea. Let me drop these points. Yeah, now it should be fine. So the graph should be like this, and then it's going to get steady at 2.5. Remember, you don't have to be super accurate there. They're more concerned about how you make your graph. So this is Hall voltage. Now the Hall voltage is replaced by a flat coil. Let's talk of coils. For coils, Jawano, listen to me very carefully. They're very confusing. I don't know why, but it's actually very simple. Coils work on EMF. EMF is only when you have a flux change. When your field changes. So EMF will only be induced when B is changing. When is B changing? B is changing in this part because Hall voltage is also changing. So there will be an EMF over here. But will there be any EMF in this part? No. Why? Q. Because Hall voltage is steady. So magnetic field strength is also going to be steady. So why will it change? It won't. So that's the first question that they ask. Show that the EMF induced at t equal to 0.01 is this. So EMF formula is delta phi by delta t. Delta phi is NBA, number of turns, flux density, area. Number of turns, 3000. Flux density given 4 into 10 t is equal to 0.01. Let's go and have a look at 0.01. 0.01, the flux density is 2 into 10 to the minus 6. I was making a mistake. I was not reading the time. At 0.01, the flux density is 2 into 10 to the minus 6. So you put 2 into 10 to the minus 6. area 3.4 10 to the minus 4, plug it in, divide by the time 0.01, and your EMF is 2.0 into 10 to the minus 4. Voila, you have the right answer. Now, very important. For till what time will you have EMF? You will have EMF as long as your field is changing. So field is changing constantly. It's a uniform change, uniform. So EMF will be a flat line from 0 till 0.02. Have a look. From 0 till 0.02, this is 10 to the minus 4. Did we not calculate EMF as 2 into 10 to the minus 4? Yes, we did. So it will be 2 into 10 to the minus 4 all the way till 0.02. Do you understand? Then what happens? Then your field becomes steady. Because your field becomes steady, there's no change. Hence your EMF goes to 0. So it's going to be 0 for the next 0.02 seconds. Then what happens? Look at the graph. Go back from 0.04 to 0.05. What happens? From 0.04 to 0.05, there's a flux change again. So because there's a flux change again, hence there will be an EMF induced, but the direction will be opposite. Here the field strength was increasing. Here the field strength is decreasing. So EMF will reverse direction. Lenz's law. So EMF will reverse direction. And you are going from 4 to 2. So you can calculate what that change will be. So you have a change of 2 into 10 is to the minus 6. So if I come back here, this change is still 2 into 10 is to the power minus 6. So the EMF drop should be of 2 into 10 is to the power minus 4. So EMF should be the same because in your graph, you came from 4 to 2. So what is the change? It's 2 into 10 is to the minus. This is the change in the field. Now you go back to your EMF formula. In B, it is still 2 into 10 to the minus 6. What is your EMF? It's 2 into 10 to the minus 4. So your EMF from 0.04 to 0.05 is 2 into 10 to the minus 4 because everything is the same. Only the direction has changed. So therefore, now you will have a downward line over here, and this is due to Lenz's law, and this was only for 0.01 seconds. So from 0.04 to 0.05. And then again, your Hall voltage becomes steady, your magnetic field becomes steady, as you can see. Therefore, there will be no EMF induced, and hence it's going to be a flat line all the way till the end. I hope that this is clear. Now, question number 8. What it is meant by a photon? Definition, wrote, learn. Quantum of energy of electromagnetic radiation. When the surface of a metal is illuminated with EM radiation, electrons are sometimes emitted. What is the name of this effect? Photoelectric effect. It is observed that this phenomenon only occurs when the frequency of the EM radiation is greater than a certain value. Regard how does this observation provides evidence for the existence of photons? Look, first of all, the electrons that are coming out from the metal, the electrons, see, this is the metal. The electrons, in order to come out, need a certain minimum energy to be emitted. So there must be some minimum energy that comes in, and that what is that minimum energy? That is the work function of the metal. So the electrons need some minimum energy to eject from the metal surface. Now if your photons, which are here, the packets of discrete energy, or quantum of energy, of quantum means packet defined. So energy, if the energy of this photon is meeting the criteria that it's equal to your threshold, the least requirement, naturally your electron will come out. And if this photon has more energy, the electron will come out with great energy. Now the energy of this photon is dependent on its frequency. So it is said, it is observed that this phenomenon occurs only when the frequency is greater than a certain minimum value. So the energy of a photon is proportional to its frequency. The higher the frequency, the higher the energy of the photon. So when the electron absorbs this photon of very high energy because the frequency is high, it gets ejected. And when does it get ejected? When the energy of the photon is greater than the minimum energy need to eject. Same. So 3 marks, you have to explain that the electron requires a certain minimum energy. The energy of the incident photon is dependent on the frequency, and the electron absorbs the photon and is emitted whenever the energy of the photon is greater than the minimum energy required to eject. Part C, you have this graph. Remember, behind all graphs, there is an equation. And behind this graph, the equation is E is equals to phi plus Ek max, which is the photoelectric equation. Now, E is the energy of the photon, which is HF. How do I know that I have to use HF or HC over lambda? Look at the axis. It's HF, frequency. So HF minus phi, you bring phi to this side, is equal to Ek max. Now, over here, you've written Ek max. So Ek max, again, linearization. Ek max is on the y-axis. Frequency is on the x-axis. So what does the gradient of this graph give? Now you can tell y is equals to x. If x is written here, what should be with it? M or c? It's always mx plus c. So the gradient of this graph gives you h, and the y-intercept gives you what? It gives you minus phi. So the gradient is Planck's constant, and the y-intercept is the negative work function, minus phi. And question number 9. Fluorine 18-9 is a radioactive nuclide that is used as a tracer in PET scans, and fluorine 18 decays to a nuclide of oxygen R8, and X is something that is formed, or maybe X is something that you need to know. When they say that this is positron emission, so that means that X is a positron. So what is the symbol for X? It's B positive. That's the symbol for positron. And what is positron? Positron is the opposite of electron, so it's going to be 0 plus 1. If it was an electron, it would have been 0 minus 1, which is also a beta negative particle. Now, what is meant by tracer? It is the material that is introduced or injected into the body, which can be absorbed by a tissue, and it is unique for every tissue. So depending on the type of tissue, the tracer has to be changed. And this tracer is the thing that carries the radioactive molecule, which goes and binds itself to the tissue that is being explored. So basically, tracer is injected into the body, and it's made in a way, it's called tracer because it has to trace or hit or bind to the tissue. When it binds to the tissue, then the tracer is like a car, and inside the car you have this little ball of radioactive nuclei, which then does the magic. So fluorine 18 is carried by the tracer. Explain how the radioactive decay of fluorine 18 results in the emission. So fluorine 18, when it decays and it forms a beta positive particle. This beta positive particle interacts with the electron. You have to know this equation, the equation for annihilation. When the beta positive particle interacts with a beta negative particle, I just told you that this is an electron. What's going to happen? If this is 0 plus 1 and this is 0 minus 1, imagine what's going to happen. It's going to become 0. So you'll have 2 gamma ray photons being emitted in opposite directions, so that momentum can be kept conserved. Remember, 2 gamma ray photons are emitted, and they're always emitted in opposite directions because the momentum has to be conserved. And beta positive particle meets with the electron. This is annihilation, and the mass of the particles, the colliding particle, is what gives off the energy. Explain how the detection of gamma ray photons is used to produce an image. So basically, if this is the tissue inside which this is happening, the gamma ray photons are detected by this ring around the patient, and the gamma ray photons arrive in opposite directions at the ring, and that helps us in figuring out the location. So the location is this. If the gamma ray photons have come from here and here, it will help us give a location. If the gamma ray photons have come from here and here, it will give us the location. So it helps in the location, the arrival time, and the image is built up from the tracer concentration inside that tissue. So once you have the location, then you have the image of the concentration of the tracer, which helps us build the image. The half-life of fluorine 18 is T. A patient is injected with the amount of substance N of fluorine 18. Determine expression for the initial activity. So look, when if you get this sort of proof, and you're not sure where to go about it, from where to start, just think about the definition. Think about the equations that you know. You already know that what is activity. Activity is n lambda. They just given a different name for activity, r naught. You can write r naught. R naught is equals to n naught. Now they're asking you for an expression in terms of t. Let's say you don't know. What is lambda? Do you have t in it? Yes. Lambda is ln2 over half life, isn't it? You know the formula. Lambda is ln2 over half life, and half life is t. So ln2 over t. I guarantee you that if it's a 3-mark question, they'll give you at least 1 or 2 marks. Even if you're not able to join it at the end, and you're able to get it to this stage, you're getting 1 mark at least. So at least get 1 mark. Don't lose 1 mark, or just don't get a 0. If you go one step ahead, n, the number of particles, they're saying has to be linked to Avogadro's number. So you know that the number of moles is the number of particles divided by Avogadro's number. So the number of particles n naught or n can be written as number of moles into Avogadro's constant. So this is number of moles. This is the formula in chemistry O levels. Number of molecules and Avogadro. This is also used a lot in ideal gases. So you have found out that n can be written as n into Na, which leads you somewhere, because n is the amount of substance, number of moles, into Avogadro's number. So n into Na comes over here, and now one step that you have to remember is, and this was the trick, that I told you that 2 gamma ray photons are emitted, not 1. It's called pair production. That's why you have to multiply it with 2, because this formula is giving you the activity for 1 gamma ray photon. You've got 2 of them, so you have to multiply this with 2. Next, on the figure, you have to sketch the graph of how the activity goes on with time. So t was the half-life, so r naught is your initial activity. So at t, it should be r naught divided by 2. So you get a point over here, and then at double the time, which is 2t, it'll be r naught divided by 4, which is this point, half of that. So next is that you just join them with a curve like this, and that's it. That's the question. And the last question: why is the statement law? Again, definition. You have to memorize. No ifs, no buts. No that I forgot. No. Why is the statement law is simple. Lambda max is inversely proportional to temperature. Lambda max is the wavelength at which maximum emission rate occurs. So this is that wavelength which has maximum emission rate from a star. Like for example, from the sun, we know that yellow light is the maximum. All wavelengths coming out. But what's the dominant color when you look at it? It's yellowish. And that's how we know what the temperature will be. We use one. Do you think we used a thermometer? Like somebody took a thermometer to the sun and figured out, oh, the temperature of the sun is 5,000, 6,000 kelvins. No, that's not possible. So what we do is, we get roasted on Earth, and we're so far away from the sun. Imagine going to the sun with a thermometer. So how do we know what the temperature of any body is? We look at their dominant wavelength. Dominant wavelength is the wavelength which has maximum emission rate from that star. It's like a Boltzmann distribution curve, but slightly different. Like it's like this. So there's one particular wavelength which has, so if you have intensity over here and wavelength over here, this is that maximum wavelength which has maximum emission rate. So it's, lambda max is not the maximum wavelength. There are more wavelengths being emitted, but this is that wavelength which has maximum intensity. Remember this. A cosmology student observes the electromagnetic radiation received from a star in a galaxy. The student uses Wien's law to estimate the surface temperature. What is meant by standard candle, object of no luminosity? You should know this. State the reason why the radiation from the star is redshifted, because the star is moving away. That's the cause of redshift. And the true values of the quantities observed or estimated are those that are corrected to allow. Allow for redshift means that if this is your actual pattern, allowing for redshift means letting them move to the red end of the spectrum. So this is the line emission spectrum which you do in quantum theory. When you say that allow for redshift, or what is the true spectrum is red shifted. However, the student does not correct for redshift, which means he's not thinking that the star is moving away. So that means he is looking at this spectrum. So place one tick that this student's uncorrected value, is it too low or is it too high? It's the student is here. The true value is this. So is the true value more or less? The true value is going to be more. So his value, the student's uncorrected value, is less than the actual wavelength. So too low. Because look, this is what the student has given us. Actually, what is happening is this. So that's why I wrote violet over here and red over here. Wavelength increases in this direction. So lambda is maximum towards the red end. So when you say red shift, these lines, these spectral lines move towards the red end. They move towards the red end. So they go towards a higher wavelength. So if you have not corrected them, would your value be lower or higher? Is this value lower or higher? This value is definitely lower than this value. This value is lower than this value. This value is lower than this value. So your wavelength that you're writing in your answer is going to be lower. Now, if you're writing a lower wavelength, lambda and temperature have an inverse relation of Wien's law. If you're writing a lower wavelength, would your temperature be, the temperature that you would give us would also be wrong? And would the temperature be low or would the temperature be high? The temperature will be very high. The distance to the star. Now the distance to the star is F is equals to L over 4 pi d square. Has nothing to do with this. So the distance to the star is the same because the luminosity has not been measured incorrectly. The radiant flux intensity, there's no mention of it. So the distance to the star has nothing to do with wavelength and temperature. So that's why that remains unaffected. The radius of the star will be affected because you know Stefan's law is L is equals to sigma A t raised to power 4. You remember that? Now, luminosity is constant. Sigma is constant. What is the relationship between area of the star and the temperature? Inverse. And the temperature that you're measuring, the surface temperature you're measuring is too high. If this is too high, the area of the star that you're probably thinking of is going to be very low. So the radius of the star is going to be low. And you know the formula for area is 4 pi r square, the surface area. So the radius of the star is going to be small. And that is the end of the chapter, or the end of the paper. Best of luck, guys. If you like the videos, make sure you like, subscribe, share with your friends. And also, please leave comments. It always helps me to improve the content on the channel. And anything that is not clear, and if somebody can give timestamps, that would be amazing. Thanks a lot.